Thanks for the opportunity. Very excited to be here. Last year, I was here on stage with SoftBank. This time, very privileged to be here with our partner from Mitsubishi Chemical, Shu Kanno-san. I will be presenting I'll be doing the first half of the presentation. Kanno-san will do the second half. And this is specifically about a quantum chemistry use case. For those of you who don't know Q-CTRL, my colleague, CEO founder of Q-CTRL, Mike Biersak, was on stage earlier talking about one part of the company, which is quantum sensing. And I'm here to talk about some of the work that we've done in quantum computing, which is the other part of the company. Specifically, we build AI-powered error-reducing infrastructure software. As you saw in the last talk, everyone is worried about error and noise in quantum hardware, and that's the number one thing that we went after in the company. And we have made tremendous strides. We were one of the first in the industry to have a purpose-built product. And what we cover are the three layers above the hardware. As you can see the quantum computing stack on the right side, you've got physical hardware at the bottom, and then you have the three layers of infrastructure software that we almost pioneered in this industry, including firmware, compiler, error correction. And then you have the algorithms and applications and quantum computing as a service layers on top. One of the things that we want to do is, and this is really a core part of our mission, is to abstract out the complexity of the hardware. And so we have done all the hard work in reducing error and pushing the system to its absolute limit that we want researchers like Similar and GIJ and many others, Fixstars, there's several others. We want them to focus on the problem and add utility. The next few slides, I'll talk about how we achieve some of that. The particular product that we use in this case study is called FireOpal, and FireOpal is the industry's premier error suppression software. Error suppression is along the same lines of error mitigation, but is foundationally different. That it has, what we do is we pre-characterize the system, and we use our very, very deep knowledge of the hardware to suppress errors at runtime. Because of this particular method that we follow, there is no post-processing. And that makes the execution much more accurate. You can run larger circuits, and obviously you can do this at much reduced cost. As you know, accessing quantum computers is not cheap, so cost is also a large consideration. And some of these numbers that I speak about are referenced in the benchmark provided in the link below. FireOpal has been released for a few years now. This is not the research code, but this is professionally engineered product code. It's been out there for a few years. And we've got dozens of customers using it. And I reference three customers on the right side. Capgemini, that used it for a drug discovery problem. Capgemini is a well-known consultancy. SoftBank, I was here last year to talk about a network service fault diagnosis problem, as well as Deloitte that looked at that used us for a logistics problem. What FireOpal is this? How do you reduce error? When people experience a quantum computer for the very first time, they experience all this noise and error. How do you go about reducing error? Well, the answer is that you have to go through a series of steps. My talk will not be very technical, but I can tell you that you have to, people start at the circuit level. You have to go through a sequence of operations, and I've listed what those are in the screen. I'm not going to read them out to you. But the important thing is not these one-off stages. It's not just about transpilation. It's not just about error mapping. It's not just about reducing crosstalk, but it's about how all of these blocks work with each other. We have put decades of research know-how, as well as years of fine-tuning and polish to make this whole thing work as a pipeline with one line of code. And we are fairly unique in this industry. We were the first to do it. We put it out there. So the problem is as such. So let us say you are an algorithms researcher. All you need to do is in your workflow, you would insert one line of FireOpal code, and with this one line, we take care of all of the hardware errors. And then push the hardware to its theoretical limit, the coherence limit. Of course, we can't do anything about that. But what our mission is to take care of the heavy lifting and allow you to stay in the problem space. And we were the first to go on IBM, and since then we have supported. We are completely problem agnostic. We are also hardware agnostic. We work with several modes of hardware. After IBM, we support IonQ, we support Rigetti, we support Oxford Quantum Circuits, and there are several others that are in the pipeline. And yeah, as I mentioned, the solver that we have is out there, and it's solving real world applications. And I've listed more customers at the bottom. UK Network Rail used us for timetable scheduling. Australian Army on route optimization. Australian Transport for New South Wales, one of the probably, I think, the first transportation agency in the world to use quantum computing, used us for transport routing as well as EV charger optimization. And also recently the Airbus BMW challenge for manufacturing and supply chain optimization. So this is a standard product that's out there that many customers are using. In this particular presentation, I'm not going to steal the thunder from Kanno-san. I'll let him speak about the use case, but let me provide an introduction. This was a quantum chemistry use case. Mitsubishi Chemical does world-class research in chemicals, serving a number of industries from aerospace and defense all the way to energy and transport. And one of the foundational problems that they are interested in is understanding the physical properties of materials, because this is what is needed for new material discovery. And when you start doing that, you are interested in how electrons behave. And obviously, the number of combinations that they need to look at scales exponentially as the system sizes grow. And with just classical computing, they've all these years they've been forced to use approximate methods. And when you have strong electronic correlations, these approximation methods suffer inaccuracies. So, but fortunately, quantum computing is arriving, and some of these electronic correlations can be efficiently represented by quantum superposition, which is why you can start to use methods like quantum phase estimation to understand how things like gap estimation problems work, which is great in principle. However, if you now start with a problem and start to run it on a quantum computer, you encounter several difficulties, right? These could be gate overheads, hardware noise sensitivity, limited fault tolerance, and fundamentally computational scalability challenges. Using FireOpal in the whole workflow transformed the utility of the quantum computer and made it useful. They saw a 5x increase in the computational capacity as defined by wider circuits over various quantum phase estimation methods, as well as over 90% gate efficiency improvement. So it's still early, but this does represent a significant step forward in the industry for solving problems in material science, material discovery, quantum chemistry, etc. So I'll pass on the mic to Kanno-san, and I look forward to what he has to say. Thank you.
Aravind, 日本語で失礼いたします。ご紹介。
Then I would like to speak in Japanese. My name is Kanno from Mitsubishi Chemical. First of all, I would like to explain what we are doing for the quantum computing. We have the R&D strategy and also business strategy and intellectual property strategy. All these three are integrated into producing innovative chemical solutions. And having said that, we have several core technologies, for example, organic, inorganic type of material research, and also process technologies, and also material characterizations. We are working on the cross-functional technologies.
というのがありまして、
One of them is computer science, and there's material informatics included there, and also quantum computing. That is how we position quantum computing. Now, regarding this study from the technical aspect, so we use the phase estimation type algorithm, and in scientific calculation, this is one of the well-known algorithm known expected to have the exponential behavior, and we use tensor to reduce the gates so that it could be carried out in ISO device. And so we made this Hubbard models as a simple electron system model, and also octatetraene was what we applied that to. And here the max was 33 qubits and 70 qubits, but actually this includes one ancilla, so they were 32 and 16. They used to be just several bits before, so now the scale is up to 5 times. And of course, we had this tensor network and phi-alpha were also used, and these were, of course, contributing factors. So for 2-qubit gate, CZ gate, the number was reduced from 7,000 to 790. So the reduction rate was like 90%. So this was a major leap in terms of the efficient scientific calculation. So this is the details. Now we used this time quantum phase estimation for science and for chemistry, sorry, and then specifically we use this Bayesian type QPE. Using this algorithm, this epsilon, which is phase, is assessed, evaluated, and this epsilon relates to the energy, and then you see the n system qubits and also answer qubit shown here. And we first prepare the state, and then we have the control time evolution tied to ancilla. And then after the measurement is taken, and depending on the phase, the measurement timing is different. Basically, this will be cosine curve. And as you see on the right side in the graph, vertically, that is a probability 0. And also the phase is shown as epsilon here. And in the first iteration, we have the plot for different phases, and then you have different probability. And for those different distributions, we apply the Bayesian, and then we can have a narrower distribution, and you repeat that until we have the exact energy. One of the challenge we took up is, as in the case of other KPEs, time evolution, control time evolution is really heavy calculation. Indeed, in the past studies, in terms of system, 1 or 3 qubits, maximally it was 6 qubits. That was really the max. So the model was really small because of this very heavy calculation of control time evolution. This is regarding the algorithm that we proposed this time have 2 characteristics. One is that the use of quantum phase difference estimation. Mr. Suisaki, Professor Suisaki is proposed this. Instead of just energy, focus was placed on the difference in the phase, quantum phase. In other words, the energy gap was really focused. And also, because the controlled time evolution is heavy, we avoid that. And this excited or ground state preparation have the control. But even so, it's much lighter in dynamics calculations. This is a difficult calculation to be carried out in IBM machines. So as you see on the right side, tensor network was used so that the circuit was reduced, downsized. With this way, the state preparation will be a brick and wall type. So this is good for the superconducting computer. And again, the tensor network is used to downsize a circuit. But if you try to just try to do the time evolution for long distance, you will have a problem because there will be a calculation explosion. But here, the what is contracted is for a very short time frame, and then you add them together, you layered it, and to avoid the explosion in calculation. So we could avoid the calculation explosion we would face in classical method. And also as side effect, all these things are prepared as 0. And thanks to this, we could make the system very strong against noise. The error detection, well, to be specific, we are not using any redundant qubits, so it's not error detection in pure way, but we have some kind of similar kind of error detection, detecting or avoiding algorithm. Now, here we use the 33 qubit Hubbard model, and also we had the 17 qubits for octatetraton. And then you have the energy on the y-axis, axis shows iteration, and we have the red portion, which is a distribution. There's some unevenness, but as the iteration goes on, you can start to see the peak. At the end of the day, it was 99%, 98%, all the signals are going, so only 1% signal is left. But despite of that, still we could keep the peak, which means that it was really strong against the noise. And also 32 systems was reduced, and by using fire opal, gate ratio was improved by 90%. So using this methods, we could make a very strong step further in the scientific calculation. And this was the joint study with KO3 and SoftBank and JUSA.
Probably 40 times higher than where the industry needs to be in order to really scale, but progress is being made very swiftly. I'm going to finish our joint talk by sort of summarizing. Mitsubishi Chemical saw a lot of gains. So did SoftBank in their quantum machine learning method last year. For those of you, this is our third year at Q2B. For those of you who are already working with us, we have received significant recognition in Japan. For those of you who are already working with us, thanks a lot. And for those of you who are not working with us, either you're a researcher in algorithms or you're preparing a quantum computer, and I know we are speaking with most of you, please come and talk to us. Either contact us directly on our website or come and see either me or Mike, who's in the last row, and we would love to help you out. Thanks a lot.